Today we're going to be going over intelligent sheet metal design. My name is Roland Robles and I've been an engineer here at MLC CAD Systems for almost 13 years now. Now my personal experience is I've been in the sheet metal manufacturing business for over 25 years, and what you're currently looking at on my screen is the first sheet metal part that I ever laid out when I was about 13 or 14 years old. Now this part was laid out on a drafting board, believe it or not, I know how to use, and then transferred over to my galvanized steel, where I later formed this up using a manual shear and a box and pan brake. Now a lot has changed in 25 years for me, and probably for most of you guys that are joining in. And what I'd like to go through is some of the challenges that I encountered both back then and even today in current day design. Now, one challenge that I've always come across with is having my components precisely fit up and also maintain very tight clearances between my mating parts, specifically if I'm welding or maybe using some sort of mechanical fastener. On top of that, inherently, sheet metal parts tend to have a lot of symmetry, and they tend to have some intelligence that usually goes into the design. I like to think of this as creating things like proportionally, where we might want to drive an equation. Another challenge that I always hear when I come across my customers and I'm out in the field is people will say, Roland, we do the same thing, but we just change it a little bit. And I like to think of that as the challenge of variations in the different design that we've already created. And then obviously, anytime that we're designing anything in sheet metal, we always have to be prepared for physically making that part. So how can we have all of our data prepared for the CNC programming? Well, to handle those challenges, I'm going to be covering 5 major topics today. Those topics are going to be what we call multi-body part modeling, which is going to give us the ability to actually build intelligence between the components that are going to go together. We're going to look at tackling equations with variables. From there, we want to set up multiple variations of our design. And to do that, I'm going to use an Excel-based design table. And then finally, but certainly not least, the last thing that we want to do is we want to be able to have intelligent drawings that have all of our information for manufacturing and DXFs that are prepped for the CNC programmers. So with that said, let's go ahead and dig into this design. And what I'm going to be doing is I'm actually going to redesign this part that I did so many years ago using sheet metal and all of these techniques that I find very valuable. So let's go ahead and get into SOLIDWORKS. Now the first thing that I'm going to do is there's some standard information that I want to be able to leverage, and I'm going to set up what we call a global variable. Now this global variable is going to give me the ability to call this value in multiple locations. In this case, I'm going to set up a variable for the depth of the tray of that toolbox. Now I want the height of this tray to always be proportionate to the depth. So what I'm going to do is I'm actually going to start writing an equation right here by simply typing in enter and then calling up the previous variable. Now, as I create multiple variables here, I like to kind of organize my thoughts. So over here on the far right of the screen, I'm going to go ahead and type in a little comment. And all this is going to do is the next time I'm in here, let's remind me of what this variable is actually going to be driving. Now, this last variable that I'm going to set up is going to be the standard length of a flange. So I'm going to be creating lots of different support flanges, and I don't want to have to type in the same value over and over. And on top of that, I want to be able to change all those standard flanges if I need to down the road. So I'm going to drive those with what we call a global variable. Now once I have these variables set up, I'm ready to start my initial design. And to do that, I'm going to start a sketch on the right plane, and I'm going to lay out some very simple lines that are going to represent the overall profile of this toolbox. Now, as I start drawing this, I'm always going to add a smart dimension. Now, you guys might already be heavy SOLIDWORKS users, but one thing I like to introduce is organization by naming your dimensions. In this case, I'm going to call this dimension depth. And I want this dimension to be driven by a variable that I've already previously set up. In order to do that, I'm going to type in the equal sign and then simply choose my variable from the list. And so what this does is this changes this from a static value to a dynamic value that's being linked to a value from somewhere else. I'm going to do the same thing over here for the height of the tray. I'm going to give the dimension a name. And then I'm going to call up my variable, again, by hitting the equal sign and then choosing the appropriate value. Now to round this profile out, I'm going to finish by drawing another vertical line and then hold Control and select these two lines and build intelligence in between them by giving them a constraint. In this case, the constraint that I'm after is going to be the equal constraint. Now, one thing that I do like to do is I like to name my sketches with appropriate nomenclature. So that way when I get back in here to modify this design, I know kind of what's driving what. So in this case, I'm going to call this a layout of tray. And then we will start our first piece of sheet metal. Now, in order to do that, we're going to start this tool called Base Flange tab, and we're going to define an end condition. In this case, the end condition is going to be an end condition of mid-plane with the value of 12 inches. Now, what I want to call note to is I'm being very precise of the way that I set this up. So when I start building a sheet metal part, I have an option to either create the material to the inside or the outside of my original profile. And in this case, I'm going to be creating a multi-body part, and I want to make sure that I make note of where I'm putting this material. In this example, I'm going to be creating this material to the inside of my base flange. Now what that gives me is that drives the overall dimensions to be the actual outside to outside of that flange. Now I'm going to come back to this sketch. So a little shortcut here is if you were to right click on any sketch, you're going to see an option called Add to Favorites. And what that does is that tags that sketch as a favorite at the top of the tree, and it gives me easier access to go and get it and modify it. Now that I have my base flange started, I need to go ahead and stiffen this part up. And in order to do that, I'm going to create what we call these edge flanges. And these edge flanges are very simple. All I have to do is select any edge that I want to put a return flange on, and then define the actual location. I can define that by simply toggling this in and out, and you'll notice that SOLIDWORKS is very intelligent, so it automatically miters these if they're going to be an internal flange. Now in this case, I want all these flanges to be the same value, and if I were to change this value, I want to change it everywhere globally. So again, I'm going to leverage that global value, and I'm going to actually start writing an equation in here. By hitting equal sign, I'm then going to choose my standard variable called f. I'll give it a quick enter, and that's going to default to that 1/2 inch. Now I'm going to set this to be an overall. That means that 1/2 inch is from outside to outside. And this is important, the flange position. This flange position drives the location of the material in reference to the edge that I selected. And in this example, I want all the material to be the inside of the edge. What that does for me is that maintains that overall diameter or that overall dimension of 12 inches from outside to outside. Now I've got a good piece of this started, but I need to finish this part by creating a second part, right? So essentially think of it as an assembly. As opposed to creating another part that is a standalone part, I'm actually going to leverage what we call multi-body modeling, where I'm going to model the second end cap in context of the first part. And this is what we call multi-body modeling. Now the benefit of this is that this gives me the ability to actually create intelligence and precise fitment between the two interacting parts. In this case, I started a sketch and I converted my original layout sketch into the active sketch by using a convert entities. Now to round out this profile, I'm going to draw 3 simple lines. Now I'd like for this part to maintain symmetry. So just the same way that I added relationships earlier, I'm going to go ahead and add a relationship here to make these 2 lines equal to each other, and then give this a smart dimension, so that way I can drive the overall height of this end cap. Now in a little bit later, I'm going to create a variation of this where I might want to change the width, or in this case, I'm going to change the height of this end cap, so that way I can sell different models of this toolbox. So I want to come back to this, but in order for me to identify this easier, I'm going to come over here to the left-hand side. I'm going to go ahead and give this dimension a name. Now you can do that from the property manager. You can also do it by simply double-clicking it and coming up here to the top. Now this top edge is going to end up being an edge flange where a handle is going to get mounted to. So let's go ahead and give this a standard value. Now I'd like for this dimension to stay proportionate to my standard flange. So again, I'm going to hit the equal sign. I'm going to choose global variables, and I'm going to choose my variable f, but this time I'm going to type in a little bit more complicated of an equation here. I'm going to say f times 3. Now the second that I hit enter and confirm this, you're going to see it's going to auto calculate this. So what I have done by setting up those variables up front is I'm giving myself that ability to call that value in multiple locations. In this case, I'm calling it not only in multiple locations on a single part, but you're going to see on actually multiple parts that are in context to each other. Now I'm ready to turn this into a piece of sheet metal. So I'm going to come back up here to my sheet metal tab. I'm going to choose base flange tab, but I want to choose this option called reverse direction. Now the reason is when I bring back my original part by hitting shift tab, I just hid that real simply by using what we call the tab command, which is an easy way to hide something on your screen. When I bring back that original body, what you're going to notice is that I designed my end cap so that way it is fitting exactly flush to the outside of the tray of my toolbox. Now that I have this done, I need to add some extra support flanges so that way this can actually be spot welded to that body. So what I'd like to do is I'd like to come over here and fire off that same edge flange that I used before, and I'm going to choose these 3 edges, this bottom edge and these 2 side edges. But what you're going to notice is that since this has been designed perfectly coincident to the body, is these edge flanges are actually technically overlapping. Well, I don't want to have to figure out any math myself. I want the system to kind of intelligently offset that for me. So I'm going to leverage what we call the flange position, and I'm going to tell the material to go to the outside of the part. So a huge benefit of using what we call a multi-body part model is that I now have the 2 parts, or what we call bodies, in the same file. So I'm not going to have to calculate what that clearance should be by toggling back and forth between multiple parts or maybe even an assembly. Now on top of that, I know that when I form these up, they're not going to be exactly perfect. So I like to account for that. And the way that I'm going to do that is I'm going to let SOLIDWORKS actually do some of the accounting for me. And the way that I do that is by turning on this option called offset, which is going to let me type in a value, which is going to give me a little bit of extra clearance between my return flange of the end cap and the main body flange that I modeled up previously. Now, on top of that, when I hit OK, matter of fact, I'm going to go back in here and I'm going to go ahead and set this to the standard value for a flange. And the big benefit to that, right, by doing a multi-body model is being able to have these 2 parts interact with each other. And so what do I mean by that? Well, if we were to come back over here into my equations and right click on it and choose manage equations, you're going to see here's my global variable. Remember, this variable called D is equal to 8, which is the depth of the tray. What I'm going to do is I'm going to change that from 8 and I'm going to change that to 10. By doing that, we're going to notice that the height's going to stay proportionate. So now the height should grow to 5. And maybe I don't like the 1/2 inch. I'm going to change this to 0.625. So we'll say this is going to be 5/8. The second I hit OK, what you're going to notice is that since I'm driving all of these equations into the sketches and into the dimensions, everything is going to stay automatic and proportionate to each other. On top of that, if I were to scroll in right here, we're going to see that my clearance gets maintained between the 2 parts. Now I'm going to go back in here and I'm going to modify that and return those values to the original values because that's really what I want them at to start with. So we're going to return that to 8, return it back to 1/2. We'll hit OK, and then we're going to see everything auto adjust. Now I'm almost ready to create the second end cap, but before I do, I'm going to add a few other little details. One of those details is going to be adding a return flange over here, and you guessed it, I want this to be the standard value, so that way if I wanted to change this, it would change it everywhere. I want to make sure that this stays flush to the top, so I'm going to let SOLIDWORKS do the thinking for me, and I'm going to keep the material to the inside, and I really don't need any extra clearance. I'll turn off that offset. Now the second I hit OK, we can see my return flange gets created, and I'm now ready to set up what we call a mirror. Now when you're working with multi-body parts, you can think of these bodies really as discrete parts that have been modeled up in one single file. So in this case, what I like to do is I'd like to take the right-hand side of this part and let's go ahead and mirror it to the left-hand side. Now, when we do that, you're going to notice that there's actually three options when doing a mirror or a pattern. There's what we call features, faces, and then one of my favorites when working in a multi-body part is what we call a body mirror. And what that gives you the ability to do is take a chunk of material and move it or copy it, in this case duplicate it, to the opposite hand side. Now I'm going to come back in here and I'm going to create what we call a design table, which is going to give me the ability to create variations of the design. But there is another sketch that I want to rename so I can find it easier. And that's going to be this sketch that I used to create that base flange. And I'm going to call this sketch InCap Layout. And in order to find it easier, again, a little shortcut that you can do is by right-clicking on anything in your feature tree, you can say Add to Favorites. And what that's going to do is it's going to tag it to the top of the tree, which will make it a little bit easier for you to find later. Remember, double-clicking on any sketch or any feature is going to bring up those dimensions. And double-clicking on the dimension is going to give you the ability to edit it. Now, we've almost got this designed whipped into shape, but there is one last thing that I need to do, and that's go ahead and add this handle. Now to add this handle, I'm going to start a brand new sketch on the right plane. But I'd like for this handle to stay perfectly coincident and adjacent to those end caps. So that way if I were to change the height or change the width or change the depth, this handle is going to always proportionately update. So one way that I can do that, since I'm inside a multi-body part, is I can leverage that geometry from the existing body. In this case, I'm going to choose this inside edge of that flange, and I'm going to hit Convert Entities. And when I do, it's going to take that flange and it's going to turn it into a sketch on the right plane. At which point, I can now start designing my sheet metal part that's going to represent that handle. Now, the thing that I love about working in the multi-body environment is being able to create extrusions and cuts and other pieces of sheet metal that are linked to your original bodies. In this case, I'm not quite sure what the inside measurement is off the top of my head, so I'm going to use an end condition called up to surface, and I'm going to drive this piece of sheet metal up to the inside edge of the first end cap. And then I'm going to do the same thing to the opposite side. When I hit OK here, what you're going to notice is that this piece of sheet metal now is perfectly mated up and is now the exact width of my toolbox from left to right. Now, when you are working in a multi-body environment, you can always focus on any discrete body by simply right-clicking on it and choosing what we call the isolate command. And what that does is it just visually hides everything else that you're seeing, and it kind of makes it look like you're in a normal single body part. And in this case, what I like to do is go ahead and finish up this design. Now to do that, I need to put a couple more return flanges on the ends, so that way I have a place to spot weld. I want these flanges to maintain the standards that I've already set up. So again, leveraging the equal sign gives me the ability to grab that global variable. And I want to make sure that that flange material is to the inside of the part. So that way my handle stays flush to the inside of the end caps. I'm going to add a couple more flanges, maybe one on either side of this. Again, using the same standardization. And in this case, I don't want those to be 90 degrees. I'm actually going to offset those in to give it a little bit of a more smooth handle for the user. Now, when I hit Exit Isolate, you're going to notice that everything maintains. And if I were to make any design changes, for example, coming back into my equations, if I wanted to change this from, say, 8 to 12, we're going to see that everything is going to automatically update. Again, the benefit and the big value, right? The value add to this, as opposed to doing these all as standalone pieces, is that my parts are now interacting together perfectly and precisely. Now, to make sure that I didn't accidentally foobar something up and type in a wrong value or miscalculate on any of my inputs, let's go ahead and let SOLIDWORKS evaluate this, and let's look for any interferences to see if any of my sheet metal thicknesses are overlapping with any other pieces. To do that, I can go to Evaluate. I can choose this option called Interference Detection, and then I can hit Calculate. And if I did everything correctly, which I did, you're going to notice that this says no interferences, meaning none of my parts are overlapping or colliding with each other. Now, what have we looked at so far? We've looked at creating what we call multi-body parts. The benefit to that is that these pieces are now interacting with each other. We've added a lot of intelligence into the model by leveraging what we call global variables with equations. In this case, we have a variable for the depth of our tray. We have the height, so that way the height is always staying proportionate to the depth. And we have a variable that's giving me the ability to use what I'm calling a standard flange. That way, if I needed to change this value, I'm not having to edit in multiple locations. Now, we're almost ready for manufacturing, but our sales team sometimes comes to us at the end of the design or the end of a project, and they say, hey guys, this looks really good, but we have another customer that wants to order something that is very similar to this, but just a little bit different. They want to create a variation. So how can we do that without recreating all of the work that we've done? Well, the first thing I'm going to do is I'm going to go ahead and hit save, and I'm going to give this a part number. So I'm going to say this is my new MLC 1500 series toolbox. Now, I've tagged these as favorites up here. And the reason that I tag these as favorites is because I'm going to leverage these to create what we call a configuration, which is a way to think of another iteration of this model. And the configurations that I'm going to be creating are going to be driving the overall width of my toolbox and the overall height of this toolbox. Right? So again, we're going to be changing the overall height and overall width of these items. Now, those dimensions are going to be this 12-inch dimension right here. Right, so I'm going to actually give that a name. I'm going to call this width toolbox. That way you can easily identify it here in just a second. And we've already set up our other dimensions. So now, how am I going to do this without having to hit File, Save As, or Pack and Go, or all sorts of crazy things? What I like to do is I'd like to leverage the power of an Excel table. I'm going to hit Insert. We're going to go down here to Tables, and we're going to use this option called Excel Design Table. Now, when I choose Excel Design Table, I'm going to tell SOLIDWORKS to go ahead and auto-create me this Excel table, and I want it to use all the parameters that I've already built into the model to generate what we call a configuration. When I do that, it's going to start my Excel table, and it's going to ask me for the dimensions that I'm going to be changing from variation to variation. In this case, I'm going to choose the depth. I'm going to choose the height. We'll go ahead and choose the width of the toolbox and the height of the end cap. Now, I'm doing this by holding Control on my keyboard and selecting all the appropriate dimensions. And once I hit OK, what SOLIDWORKS is going to do is it's going to start an Excel table for me, and it's going to put those values in columns, and it's going to give me the ability to add more rows to these columns. And every time I add a row, it's going to add what we call a configuration. Now, I'm going to add, for the sake of the example here, I'm going to add 3 variations of this. I'm going to say I'm selling now a small toolbox, I want to sell a medium toolbox, and I want to sell a large toolbox. Now, these, you can see, are being driven by a variable, but these are being driven by static values that I'm going to want to change. Now, all 4 of these are going to start off as the same, so I'm going to use just standard Excel commands, and I'm going to copy these, and then once I have them copied, I'm going to go ahead and change the things that I want to change. For the small toolbox, I'm going to make this a little bit more narrow. The medium toolbox will leave at 12, but I'd like to change the height of the end cap to say 10. And for the large toolbox, I'm going to go ahead and change both values. I'm going to make it larger in both width, and I'm going to make it larger in height. Now, when I do that, the second that I click off of that, it's going to go ahead and save that design table, and it's going to create those configurations. Now, if you've never seen a configuration before, the configuration is actually managed in what we call a configuration manager. And what this is doing is it's giving me the ability to iterate in the same file that has all this intelligence into it to create more part numbers, which in turn will generate my flat patterns that I'm going to need. Now, let's go ahead and see what SOLIDWORKS did for me here. If I double click on any of these configurations, it's going to activate those configurations, and you're going to notice that these models automatically update. Since I leveraged a multi-body part and I designed these in context of each other, all of my clearances stay maintained. All of my interferences should still be no interferences. And all of the intelligence is built now into a single file, which I can use and leverage to create multiple iterations of this much quicker and much more efficient than previously before. Now, if you're thinking to yourself, well, Roland, that looks great, but I need a drawing of each one of these configurations, and also I need flat patterns and DXFs. The beauty of this is multi-body parts act very similar to a standard sheet metal part with regards to I can flatten any of these bodies by simply clicking on them and choosing my flatten command. I can also create drawings from any of these configurations or any of these bodies, and that's what I'd like to do next. Let's go ahead and round out this project by creating the manufacturing information that we know we're going to need. And the two main things that we're going to need is we're going to need a detailed drawing with all the dimensions, and then we're going to need DXFs that we can then send over to our CNC guys so that way they can actually cut these out. So let's go ahead and get our drawing started first. I'm going to come up here and I'm going to say, let's make a drawing. And in this case, I'm going to use one of my standard C-size templates. Now, when I do that, I can always use my view palette. But in this case, what I like to do is I like to use the standard model view. So you're generally going to find that up here at the top. Now, the reason I like to do that is because if I'm creating a drawing and the part has configurations, this gives me the ability to easily identify what configuration I want to use. In this case, I'm going to use my default configuration, and I'm going to create my 4 standard views just really quickly. Now, on top of having a standard drawing that's going to show this part all welded together and assembled together, I also need drawing views of each one of those bodies flattened out. So I'm going to add a second sheet in here. I'm going to come back over here to my model view. We're going to go ahead and hit next. We're going to use our default configuration, which is the configuration we started with. But you will notice that I have this option called Select Bodies. This gives me the ability to define a scope which they can flatten out, which turns this into essentially a standard single body flat pattern. At which point I can add my manufacturing information. A lot of the times I like to leverage an ordinate dimension, and I can detail out all of my bin lines so my press brake operators can now come in here and calculate their backstop gauges. Now, the benefit to this is off this single flat pattern, I can create multiple views. So if you said, well, Roland, I'd like to see a projected view that shows that one body formed up. No worries. All I have to do is project that flat pattern. And then once I have that thing projected, I can simply choose my configuration of this thing formed up. At which point it's going to show me that single body formed up. And then I can come in here and add any appropriate dimensions that I might want to convey down to the manufacturing or the quality team. Now let's look at that one more time. You might say, well, Roland, well, how'd you do that? Again, I want to create a third sheet, but this time I'd like to create a flat pattern of the end cap. So if I come in here, I'm going to choose my model. We're going to choose this option called Select Bodies. In this case, we're going to choose this end cap. And then we're going to simply tell SOLIDWORKS to go ahead and flatten this out. And again, what this is doing is it's generating a flat pattern off that single body. Now, you don't necessarily have to put all these in different views. So sometimes I see customers want to create one kind of like master drawing. You absolutely can do that. So if I come in here and say I wanted to include the um, include the handle in here, I could do that also. So we'll go ahead and give that a little flatten, and we are getting really close to manufacturing. Now, for the sake of time, obviously in a normal production environment, I would probably come in here and detail these out with all the appropriate dimensions. But in order to kind of keep this ball rolling, I'm just going to kind of give these some rudimentary or rough dimensions. And then I'd like to go back to my first page. And you say, well, Roland, I already have this. It's kind of like an assembly drawing. What about a bill of material? Can I add a bill of material in here and put call outs and put quantities? Now, you absolutely can do that. And we call this a cut list. But before we do that, I'd like to show you something that is unique to what we call a multi-body part. When you're working with multi-body parts, whether this is in sheet metal or weldments or any kind of standard part, you're going to notice that it's going to create this thing called a cut list. And what this cut list is doing is it's generating a lot of the manufacturing information that we already need in the background. Things like the bounding box, the area, the amount of cutting length on the outer or inner, the amount of bends. And then there's some other unique information that we can leverage to our advantage. And one of those things is the description. And this description is for that body, or some people like to think of it as a part. In this case, I'm going to give this a description. I'm going to call this a toolbox tray. And I'm going to do the same thing for the other three components. In this case, we're going to call this a end cap toolbox. And then for my last item, we're going to call this handle toolbox. And so what that's doing is you can almost think of these as piece parts. But instead of being an assembly, they're what we call bodies in a multi-body part. Now, the benefit of doing that is when I get over here to the drawing, right, we've already looked at creating multi-sheet drawings for the flat patterns, but what about for the finished good? Well, you can treat this very similar to the way that you create an assembly drawing with regards to I can come in here and use a table and I can add what we call a cut list. When I do that, it's going to create items, quantities, descriptions. This is sheet metal, so there's really no link. So I'm going to clean up this by just right-clicking on there and deleting. And then I can add all the normal things that I would do in an assembly drawing. For example, creating things like balloons, maybe adding some dimensions into the assembly drawing. I want to come in here and give this a weld call out. Or any other ancillary annotation. Now, a multi-body drawing is no different than creating a drawing off a single part, or maybe even creating a drawing of an assembly. You can add dimensions, you can add your annotations, you can add your tolerances, and any other appropriate information that you deem necessary for your manufacturing. Now, to wrap up this design, the last thing that I want to show and kind of show and teach you guys is preparing this for CNC programming. Now, in my experience, most CNC programs are going to take in, at the bare minimum, what we call a DXF file. Now, how do I take this out and export this out to a DXF? Well, it's very simple. If you right-click on any one of these bodies, you're going to see an option right here called Export to DXF. When you do, it's going to ask you to save this in a location and give it a name. So in this case, I'm going to give this a name of MLC-1500 tray flat DXF. And then we'll go ahead and hit save, and it's going to let us choose our options. Now in this case, this is a piece of sheet metal, so I'm going to turn on the option to save this DXF as a sheet metal, so that way it flattens it out. And I would like to add what we call the geometry and the bend lines. Now the challenge with doing that is most of the CNC tools that I used to program with needed all of their geometry on what we call different layers. So what SOLIDWORKS gives you the opportunity to automate is what we call DXF mapping. And so what this does is I've predefined that all my outline get mapped onto a layer called outline, and get classified with the color of blue as a solid line. And my bend lines, which is where the press brake would be needing generally to strike the part, is going to get classified on a layer that's red with a different line style. And so what this does is that eliminates that need for my CNC programmer to then go and have to actually modify the DXF that I'm sending him, which is usually a big thing, especially if you're doing things like water jet or even laser cutting, because if something is on the wrong layer, usually it's going to get cut with the wrong algorithm. So to wrap this up, what have we looked at today? We looked at leveraging multi-body part modeling to build intelligence into parts that should interact with each other. We added what we call global variables, and we created equations so that way we could have intelligence built into our tray body and also our end cap. We leveraged an Excel-based design table to create multiple iterations of this, which we call a configuration in SOLIDWORKS. And then finally, we automated the flat pattern drawing by leveraging our multi-body part and creating our 3 discrete sheets for each body, and then exporting it out using SOLIDWORKS to map the appropriate information into different layers for our CNC program. I hope you found this session informative and educational. Thanks again for joining, and I'll be sticking around to answer any questions that you guys might have.